So I'm Adam.
I'm Chris.
And this is Android Suspenders. Today we're going to talk a little bit about Kotlin coroutines. But to get started, a little bit of background. Many of you are probably familiar with us already, is the idea of Android's main thread. And just like almost every other UI toolkit out there, Android exposes a single UI or main thread for doing updates to parts of your UI. So some of the things that you might find yourself doing on the main thread: inflating views. You could be doing measure and layout operations to change the shape of your view hierarchy. You could be drawing, or many other things, really, like processing input events, and so on and so forth. So today, you're probably familiar with this 16 millisecond time limit. The vast majority of devices out there have a refresh rate of 60 hertz, which means that you have just over 16 milliseconds to do all of the work necessary in order to deliver a smooth frame rate. So what happens when that display rate goes up? So 90 hertz means you have 12 milliseconds. 120 hertz means you have 8 milliseconds. And you have less and less time to get some of this work done. If you take a look at a systrace, you'll usually find that the things that cause you to miss a frame and thereby have kind of jank in your application is really app code. Like if you're binding items to a recycler view, reading from a data store, so on and so forth, these are all bits of work that it would be really great if we could keep this off of that main thread and out of this critical path. So how do we fix it? Well, this talk isn't about achieving 8 millisecond refresh boundaries. This is about making use of the resources we have available. And all the phones that we have multiple cores in them today. So how do we actually make use of that? Well, some of you probably remember this thing. It's been around for quite some time and has a lot of issues. It composes a little bit badly, has some issues around rotation. It's really easy to get wrong. There's executors, which most Java developers are familiar with. And this kind of lets you share some thread pools, which is nice. But it's otherwise kind of a really raw API. You can build things out of it, but it's not really convenient to use on its own. Loaders. Loaders are a thing that were certainly out there that solved a few problems, but it was pretty narrowly scoped. It's really now deprecated, so there's not a whole lot there. We can use futures. There's listenable future, which has started showing up in more Android X APIs. But you may not want to pull in all of Guava and all of the infrastructure that really helps you leverage some of the things that you can do with it. And unless you're working on MinSDK 24, you can't use completable future either. And really, there's a whole bunch of other reasons why you might not want to use that to begin with. So there are a lot of other libraries out there. I mentioned Guava. Guava is certainly one that you can pull into your app. RxJava is super popular. It's a great library, does a lot of things well. But if you're sitting here in this talk today, you're probably here to talk about coroutines, which is a new feature that went fully stable in Kotlin 1.3 just this fall. So why should we use them?
Great. So when I think about this question, I'm thinking about what does your typical mobile app do? And I think for the most part, you can describe them as kind of CRUD apps. And I don't mean the American slang. I mean the fact that they create, they read, they update, and they delete data, usually to some kind of local data source, like a database or whatever it be. And then going a bit further, a lot of apps will also have some kind of sync. So they'll upload data and pull data back from some kind of web service. Now, apps are actually pretty simple computationally. You're not really taxing the CPU that much, really. Yes, the logic can be quite tricky to get right, but actually, they're pretty simple. And of course, Android, we put a lot of stuff in your way. Like we make your life harder. But actually, your apps are actually pretty simple from a logic point of view. So why coroutines? Well, how do they actually fix that? Well, I think they're great for I/O tasks, especially for a resource-constrained system like the phones and tablets that you're using today. Now, you can't create a thread for every network request you ever use, because threads take in the space of about 1 megabyte to 2 megabytes of RAM every time you create one. That's why thread pools actually cache threads for you. Now, coroutines, on the other hand, take in the sort of realm of tens of kilobytes in terms of actually coroutine. They use threads underneath, but they use them in a much more optimal way. Also, in my mind anyway, they have an easier development model. It's a lot easier for developers to kind of come into a new code source, and see an imperative line-by-line coroutine over something like an RxJava chain. Like, to be able to understand what's happening there is, in my mind anyway, easier. And same thing for callbacks. Like, everyone knows about callback hell, and having to go line by line and see where you've been called and stuff. And so coroutines help, hopefully anyway, fix that. So a lot of this talk was written in mind with a sample app that I've been writing for the past 12 months or so called TV. It was originally, I went all in on RxJava. It was RxJava from top to bottom. And I've kind of slowly brought coroutines into it. It's now about 50% coroutines, 50% RxJava. So it still uses both. And I think they both have a place in Android development. And so, yeah, go use both. Now, as Android developers, we have to care about APK size and method counts. Now, in Kotlin, in my app anyway, I'm using 3 libraries from the Kotlin coroutines kind of tree. The core, which contains the majority of what you'll actually use. Android, which adds support for the Android main thread, amongst other small things. And then Rx2, which allows you to interrupt with RxJava. So if you're not using RxJava, you won't need that one, but it's pretty small anyway. Now, if you actually pull down those jar files, just from Maven Central or wherever, they would come to about 774 kilobytes. So that's quite big, and it should be alarm bells are ringing. But once you actually put that in your APK, it actually shrinks down because it's packed in, and it comes down to about 500 kilobytes. But that method references are actually still quite high. That's like 5% of your 64K. As soon as you turn on minify, and now this is just tree shaking, so there's no optimization turned on here, or ProGuard, they both have similar results. You're looking at about 113K, so a lot less. And again, the method references has dropped. But as soon as you turn on optimization, and then you go through all of trying to fix all the ProGuard rules, you're coming down to that magic value, which is less than 100 kilobytes. And again, your method references are now 834. Like it's less than 1%. Well, it's 1% of your references. Now, one thing to note when you're using ProGuard or R8 is that you need to use this rule. It's not currently bundled with the jars, but hopefully it'll be added soon. But it's a pretty simple rule to add.
Right. So hopefully by now you're thinking about how you might use coroutines in your app. So let's go ahead and talk a little bit about actually writing them. So anything that you can do with a one-shot callback or future, you can do with a suspend function. Everything with coroutines is kind of based around this idea of a suspending function as a basis for creating APIs. Suspend functions can stop and yield their thread without blocking, and they can be resumed later like a callback. And they can only be called from another suspend function, so just to set up all the machinery involved in that. But the core thing is that all of this kind of fits on one slide. There's less to remember. The rest of the language still works the same in the presence of suspend functions, and we'll spend the rest of the talk talking about that. So here's a suspending method from Chris's app. Actually, this is a data repository for TV shows. So you go ahead and you call this update show function with an ID. We get some shows, and we get a little bit more data from a remote source, and a little bit more data from a second source. Finally, we merge all that together, and we save that data. So these 3 main tasks where we spend the bulk of the time, these are done sequentially, but none of these tasks have a dependency on one another. So wouldn't it be nice if we could do this concurrently? So with the async builder, we can do this. So we're going to start from the very top here. We start by opening a coroutine scope. And this is important because this allows us to perform this parallel decomposition using the async builder. It brings a coroutine scope receiver into scope for this Lambda block that we have. So first, we build the async operation, and the second, and the third. And then we await the result of each one in turn. So the nice thing here is that we've launched all of these things, let them run kind of independently, and then we bring them back together again. So since all of these things can be now done in parallel, things should complete faster. So trying to do this with raw threads by hand would be a lot more code which you would need to maintain along the way. So the async builder is for when we want to run something and then later await the result after kind of giving it a chance to finish while we're doing something else. It's very similar to C# or promises in JavaScript. So what about when you just want to launch something and forget about it, though? Well, there's something for that, too. It's just called launch. It works pretty much the same way. So in this case, it's a lot more similar to executors and just sort of submitting a task, submitting something to an Android handler, for example, when we just want to fire and forget and deal with it later. So that's a little bit about the basics of running coroutines in isolation. How do you run them on Android, though? So in this case, you might have an Arch Components view model. And wouldn't it be nice if we had kind of an easy way to put all this stuff together automatically? We needed to be able to open a scope. So where do you get one of those things to begin with that you can launch things into? Well, in this case, our view model has a show repository, which is our data layer. And we have a view state that the view or activity or fragment can observe. We can refresh on construction. And when we actually go to refresh, we launch into this new viewModelScope extension property. This is coming very soon to the Android X libraries. Those of you who like to watch commits in AOSP might have seen this go in already. So the refresh function launches a coroutine uses the launch builder, which then calls the update function on the repository. And our coroutine resumes back on the main thread after update show returns, so we can safely manipulate our view hierarchy with the results just on the next line of code. We have this nice, clean, sequential ordering of operations. So those of you who want to go check out this thing that's upcoming, you can go to this link, take a look at the change so far in advance of the actual release. This is coming in an upcoming release of our KTX libraries. So let's go ahead and demystify how some of this works a little bit. But before we can go too deep, we need to start talking about some of the other primitives that are at work under the hood here.
OK, great. So we're going to talk about jobs a little bit. So what is a job? So here, when you actually look at this code snippet, the one we just looked at from Adam, you're actually using the launch method. Now, when you actually run that launch method, it returns what we call a job. Now, job allows us to keep a reference to that ongoing piece of work. And it has really one method on it, and it's called cancel. Now, obviously, in this example, we wouldn't just call cancel straight away after we've launched something. That would be ridiculous. But what it does allow us to do is handle something like double refreshes. Like, if you have something like pull to refresh in your app and an automated refresh, you don't want them both to happen at the same time, and then you have two things happening at the same time. So here, this code snippet, you can keep a reference to the one that's currently running. And if it happens again, like a refresh is called, then you can cancel the first one. And so that's the kind of how job kind of works. It's a very simple object, but it allows you to keep a reference of the ongoing piece of work. So you may have seen that viewModelScope thing and wondered what it is. Adam explained it earlier, and that you can have a scope, and it provides you with all the context you need to run a launch or an async. So let's take a look at how they actually work underneath. So coroutine scope is an interface that allows objects to provide a scope for coroutines. Think things like things with a life cycle, so fragments, activities, view model even. They can provide a life cycle for the coroutine itself and start and stop it as it needs. Async and launch used to be sort of global methods, and now a recent refactor brought them as instant methods on the coroutine scope. What it means is, mentally anyway, is that instead of just launching something, you're launching a coroutine on X. So I'm launching a coroutine on the activity. It just changes it mentally in your head in that it's tied to the lifecycle of something else.
Right. If you're used to working with the lifecycle owner in Arch components so far, you know the lifecycle owner has a lifecycle that you can then observe and attach things to. Similarly, a coroutine scope has a coroutine context that carries along everything necessary to know how to launch a coroutine.
Some of the stuff we're going to talk about in a bit. And similarly, coroutine scopes provide a default context. So you can provide a default context for all the coroutines that run on it. So think things like what kind of thread pool or dispatcher it runs on, the job, the parent job that allows you to cancel it later, and other things which you can add to it. It's basically a map of context. And it's crashed again.
Oh, it's a good day for slides.
It's just, I think we're back
on?
Back? OK, cool. So let's take a look at another example. This time, we're not going to use viewModelScope, the automated thing we've added to Android X. We're going to write it out ourselves. So here you can see that we've created a job. And now it's just a simple instantiation. We're just going to keep a reference to it. And then we're going to keep that create a coroutine scope using our job. And that means that anything that runs on it allows us to track back using that job object. We're also going to give it a default dispatcher. We're going to talk more about that later. But basically what it means is that anything that is launched on that scope will be automatically run on the main thread, Android main thread, in this example. So once we've done that, we have our refresh method again. And this time, instead of that viewModelScope, the automated thing, we're going to use our own created scope. And again, it's exactly the same code. We're just using a different type of scope this time. But this time, the launch we scoped to the job object we created earlier, which means that in onCleared, which is the callback we have in viewModel to actually, when it's been torn down, we can actually just call job.cancel. And that means that any coroutines which are currently running when the viewModel goes down will be canceled at the same time. It reduces memory leaks or whatever it is, just allows us to tidy up. So if you actually have a look at how things are run now, so we've launched our coroutine, and now we're going to go into our update show method. So here we are in our coroutine, so our launch, which is modeled by that blue thing going around. Now here we're in the update show method, which is denoted by the yellow arrow. So we're going to go past that first piece of code, which is the async builder. At this point, we have a first coroutine running, which is our async, and that's doing the local show store stuff. So it's running nicely, and it's doing its thing. Now, the outer coroutine is going to go past that and go past the second async, which is the remote. Here, again, so we now have 2 coroutines running, and they're both, well, we have 3 coroutines running, but 2 inner ones, 2 child coroutines. So once they're launched and they're running and going along, we forward on to the first await. Now, at this point, we're waiting for that first async, the local, to actually finish itself up and then return a result, which is what await will return. But at this point, because we're waiting on that first async, the outer coroutine is what we call suspended. It's just sat there doing nothing. But during that time, that view model has been torn down. I don't know, the activity's gone away or whatever it would be. And we've called job.cancel. Now, at this point, the outer coroutine is cancelled, and then the inner 2 are also cancelled. And now that's something that coroutine scope gives us, and scoping in general gives us for free, in that child coroutines automatically inherit from its parent coroutine. So if the parent coroutine's been cancelled, anything below it will also be. That's some of the nice stuff that's been added recently. But what if you're not actually using view models? A lot of us might not be using it, and we have other APIs which allow you to do similar type of things. So as part of the Android architecture components, we added a listener functionality for life cycles. So here's a very quick example of how you use them generally. You create a lifecycle observer, and in this example, we're using default. And when you create, it has methods for each of the different lifecycle events, so on create, destroy, stop, start, whatever it be. And to actually use it on like an activity or whatever it be, you create an instance and you add the observer. Hopefully you've seen this API before. So let's build a kind of scope-aware lifecycle observer, which allows us to scope coroutines to an actual lifecycle instance. The primary API we'll use here is that we'll pass on a Lambda, and that's the thing that we run once we've, say, been started, which is kind of what you want usually most of the time. So we'll now look at our implementation. So the first thing we want to do is on start. So that's when we'll start running our kind of piece of code. So we'll create a coroutine scope using a job, and then we're going to run it on the dispatchers.main. You can choose what that would be. And then we'll call scope.launch, and then just call our Lambda. Pretty simple, really. And then finally, and on stop, which seems like a good lifecycle to use, that we'll call, well, in that piece of code, but we'll eventually cancel the job. And that will mean that coroutine, if it's still running at that point, will be cancelled. So if you can see, that code isn't actually that complex. Like, OK, it's now in Android X, so it's not nicer to use, but if you look at the sort of deep down of it, it's actually pretty simple. And then to actually finish it all off, we'll provide a nice builder function, and you pass it to Lambda, and it will automatically add the observer for you. And what it allows us to do is stuff like this. So here we have a details fragment, and in onVCreated, we will use our livescope extension function, and then just run something. And that will automatically be started when we get to, well, it will be started when we go at start on the fragment, and then it will be closed or ended when we get on stop. That brings us on to cancellation.
Right. We've talked a lot about this idea of canceling a coroutine, but what actually happens when this thing cancels? I mean, if you just have kind of a block of code that's running, what gets torn down? What do you need to do to sort of clean up? So when a coroutine is canceled, if it's canceled while it's suspended, so it's waiting on something else to happen, in callback terms, the callback just hasn't been invoked yet, it'll throw a cancellation exception, or rather, the coroutine will resume from the point that it was suspended with a cancellation exception. So what does that actually look like? Here's our example from before. So what happens if we need to clean something up if this is canceled in the middle of that update show function? Well, because it throws a cancellation exception, this is something that we kind of know how to do already. Plain old finally blocks run as expected. We didn't have to add any new concepts beyond what we already know from the rest of Kotlin. But if blocking code is running, cancellation requires some explicit cooperation in order to stop what it's doing. So we can check for that cancellation explicitly in a couple of ways. Generally, this means checking to see if your coroutine is currently active in one way, shape, or form. And there are a couple of useful patterns for doing this. So one of those patterns is that if you know that your job is already canceled, you can call any one of the stock suspending methods, such as yield, used as the example here, to force a cancellation exception to be thrown, relying on that standards implementation that I mentioned before, that if you're canceled when you're trying to suspend, then you'll resume with that cancellation exception. So we know that this will immediately throw if we happen to be canceled. But if you're in a tight loop, you can also just check this is active that's available from any suspending scope. And you can just simply stop what you're doing. There's no reason to really involve an exception here if all you're doing is some sort of tight inner computation loop that you need to break out of. Which kind of leads nicely up into how exceptions are handled with coroutines in general. And there are a few things that are really worth pointing out, especially if you followed some of the Kotlin X.coroutines development leading up to release, because there were some really significant changes that happened. The first is that launch will rethrow unhandled exceptions as they happen. So more precisely, it fails the parent. It cancels its parent job. The parent sees a cancellation exception with the original exception as the cause in the exception object itself. So similar to a thread, they get dispatched to the default exception handler at the root of a job tree if nothing else manages to handle that. But your coroutine context also gets a chance to intercept. You can attach a special element to the coroutine context itself that you can use to handle unhandled exceptions. So let's go ahead and see how that works. Here's, again, our example from before. And say that save show throws a very domain-specific exception in this case. So in this case, this will be treated like an uncaught exception at runtime, just like anything else that throws an uncaught exception on your main thread. So async is a little bit different. If an exception is thrown while something that you launched with async is running, it'll hold on to that exception and only throw when the caller calls await. So coming back to our example from before again, let's go ahead and use what we know. We throw our exception from one of these async jobs. But that gets thrown from this call to await itself. So we know exactly where we need to try and catch that exception, just kind of in the normal way, and handle that error. But there's a gotcha here, and that's that async works the same way as launch in terms of how this nested job tree is handled. The deferred object that it returns is just another kind of job, and so it'll cancel the parent if it fails with an unhandled exception, just like launch does. And it'll do this even if we did an await and called it. Now, this is kind of important because if something throws an exception, it's really important that your app know about it. Like, it shouldn't just disappear into the ether. But at the same time, it kind of defeats the purpose of the code in this sample here. Like, we caught it. What are we supposed to do here? Well, in this case, instead of using coroutine scope at the top to open up this parallel decomposition, we can use supervisor scope. It works exactly like coroutine scope, except with a supervisor job, which is a special kind of job that won't be canceled if a child fails with an unhandled exception. Oh, one more spot. Yep. It will only be thrown from this await method here.
Cool. So earlier we mentioned that we can actually decide where coroutines are run and what kind of thread they run on. Because actually on the JVM and on Android, we actually still run on threads. It still uses a thread pool underneath, so we still can decide where that actually gets dispatched on. Now let's have a look. So here we have our launch, a very simple launch, which is missing a scope, but just look at the example. Now default actually is that the context will be using what we call a dispatcher.default. That's a default dispatcher that's kind of given for you for free, and it's supposed to be sort of default for everything, really.
It's essentially a computation thread pool if you're used to using that from RxJava.
So what is a coroutine dispatcher, which is what it basically is? Well, it's the thing which runs and schedules coroutines, as I mentioned earlier. It schedules a coroutines to run on something, on a thread in our case. Now, dispatchers.default, which is the default, which you get, is that it uses CPU count threads. So it has, say your device has 4 CPUs in it, you'll get a thread pool of 4, which isn't so great for things like I/O. So most apps will be doing a lot of network or disk or whatever it be, so it's not so great for that. So yeah, it's mostly more like a computational type dispatcher. But it's also an elastic thread executor, which we'll talk about in a minute, but it's the default. There's also dispatchers.io, which was added fairly recently, and it was designed specifically for blocking I/O tasks. So things that we really care about, network, image loading, reading from disk, database, blah, blah, blah. It uses a minimum of 64 parallelism, which basically means that you can have up to 64 tasks run at a time, which is great for what we need. So yeah, you can launch it like that. But the really great thing about the I/O dispatcher is that it shares thread pools with the default dispatcher. And the point where it becomes great is this. So here we have an example where we have an async, which is using the default dispatcher. And then we're going to load an image on the I/O dispatcher. So we're going to do some disk reading, some kind of load of image, whatever it be. And then we're going to use that result and then process it somehow. It's a computational task. Now, because this is running on the default dispatcher, there is no actual thread switch in there because we're using those shared thread pools I/O and default uses shared threads. So therefore, there's no actual thread switch, which makes it a whole lot quicker. Then we also have dispatches.main, which we spoke about a little bit already. It allows running coroutines on the UI main thread. Kind of a nuance with that is that in later releases anyway, it uses service loader to load the dispatcher in your code, which is kind of tricky when we have things like ProGuard, so you've got to be careful with this. But yeah, just be careful. And the thing you need to know is that you need to add the Android dependency, which we spoke about earlier anyway. And then to use it, it's, as we said, just launch and then dispatch.main. So that brings us a little bit onto reactivity. So how many blog posts that you've seen recently anyway can be summarized as this slide? And I myself have been guilty of this. Now, I'm going to make the premise and the statement that most devs use RxJava just because it makes threading easy. So the fact that you have schedule on and you can easily switch a thread or I'll switch multiple threads, and that's why most RxJava is uses. Now, of course, there are going to be people who go top to bottom with chains and reactivity. But I think for the 80% of the cases, it's just to switch a thread. And that's because the APIs that we have, and we spoke about them earlier, aren't so great to use. I'd say that and because of that, most people end up using things like single, maybe, and completable, because that's specifically what they are. They're single one-shot things. Single allows you to always have a type, maybe it's nullable, and completable doesn't have a return type. So they're all pretty similar. But in fact, they only actually exist on RxJava, RxScala, and RxGroovy. They don't actually exist in any other platform. So as I said earlier, then maybe it's more of a reflection of sort of the APIs that we have at our disposal rather than the fact that they're needed. So coroutines can actually quite easily replace single, maybe, and completable. They do exactly what you think. And we said earlier about replacing callbacks. They also replace these kind of quite nicely. So here's an example. So we have a retrofit interface, which has a get, and it returns a single, which just returns a list of shows. And the way you'd use that in RxJava is you'd do this chaining. So you'd switch the scheduler using schedule on. And here we're going to use the I/O scheduler, which is provided for you. And then we're going to do some calls to when it's finished. Now, the nice thing about the Rx2 interrupt library of coroutines is that you can actually use that exact single as an await. So you can actually use it as like a suspending deferred. So it's really handy for when you're kind of slowly migrating towards coroutines and you don't want to change everything from day one. You can actually keep those interfaces or those observables, and you can actually just call await on them. The receive inside can be using coroutines. So it's quite a handy way to slowly migrate. But what would it be great if we can actually make that retrofit call just a suspending function and just remove the whole Rx from the start? Well, we can. And that is actually coming to retrofit soon. Jake has a PR, which is pending review, but he tells me it's soon. So yeah, it's coming soon. And then if we look at our consuming code, it's pretty much the same. It's just we can now get rid of that await. And it's just a normal suspending function that we've called, and it's just a normal coroutine. And that brings us on to our final section, which is kind of bringing it all back together and trying to think of two scenarios where we show you how to use coroutines to make your lives easier on Android. Both of the examples are all about location. The first one is about actually getting the last known location, which you can kind of think is like a one-shot callback. So here we're going to use the Fuse Location Provider client, which is from the Google Play Services API. It's actually kind of cool because it combines all different providers we have, like Wi-Fi and GPS and mobile and whatever it is, Bluetooth. It provides all those providers for you into one single API. So it's actually a really nice API to use. And it returns a task, which is a kind of future-y type thing that the Play Services library has. And yeah, so you call client.getLastLocation, and it returns a task. And from the task, you can add what we call a complete listener, and then you'll get the result back eventually. So it's completely async. So when you think about it, what we're doing is converting a callback API into a suspending function. That's pretty much what we want to do. And luckily, the Coroutines library has two kind of builders that do exactly what we want. The first is suspend coroutine. And what you do, you pass a lambda in, which allows you to set up your callback. So basically what we'll do here is call Play Services and go, get me the last location. At that point, the coroutine immediately suspends, waiting for the result to come back, and then the callback can wake it back up, basically. So we'll go through an example now. Yeah, you're given a continuation to later resume. That's how we do it, and how you pass the result back. Analyze the call to cancel the call. Sorry, actually, that's a different one. So there is another version. Sorry, didn't mean to skip that. There's another version called suspend cancelable coroutine. It's like a little add-on on top. And it allows you to cancel the call. So say your coroutine is canceled, you can then tell the underlying API, in this case play services, to cancel its call. So let's build our function. So here we're going to have a suspending function called getLastLocation, and it returns an actual location. It doesn't return a future or anything like that. It's just a straight-up location. So we're going to use our suspend cancelable coroutine builder, and then we're going to have a continuation. That's our kind of callbacky type thing. And then we're going to sort of set up. So we're going to call a location client, which is the play services API, last location, and then we get a task back, and then we're going to add our onComplete listener. At that point, we are going to wake up our coroutine. So that is how we pass back to the suspended coroutine the result, and it then wakes up, and the suspended function basically wakes back up, resumes. Now, because this is a cancelable, actually, back a little bit. Because we are using task, we're not using the success listener, we're using the complete listener, which means that the task itself can throw an exception. Like, it can fail for whatever reason, so you don't have location permission or whatever it would be. Now, it will raise an exception on you, which means that you can populate that back up to the callee, which is done with the resume with exception method. And finally, because we're using suspend cancelable coroutine, we need to tell the play services API that we've been canceled, so therefore it should cancel. So we do that with a callback, which is invoke on completion. At that point, as soon as you know that the coroutine has been canceled, which means that you need to tell play services. Now, this API doesn't actually exist because play services doesn't have a cancel method, but imagine it just exists. Now, Adam's going to talk about observing.
Sure. So what happens when you want to observe a sequence of events over time? Now, this is the thing that Rx is really, really good at. Like, if you're using Rx for anything, it should be for this. And people tend to compare RxJava and coroutines quite a bit in blogs and so on and so forth. So what does it actually look like if we try and emulate this using coroutines as a primitive? So play services location API, in addition to letting you get just kind of a one-shot, what's my current location, it lets you request location updates using a callback that's invoked multiple times. So normally this is a prime candidate to be an observable. You register a callback at subscribe time and unregister when that subscription is disposed. We get this composable control over shutting down the updates really cleanly. So Rx is a great library, offers a ton of functionality to build things like this. So how many similar benefits can we get if we base this off of suspending functions? So let's, again, start just writing a simple function, or at least it's going to start out simple. Suspending functions don't return until their work is all done. So there's no disposable or closable returned by it, since the calling scope itself is cancelable. We just don't return until we're done. So our observer, in this case, can just be a simple lambda that accepts a location result. And we'll go ahead and call it whenever a new location is reported, without actually returning from observed location. So if you take in this giant pile of code here, some of you might notice that it looks an awful lot like an observable.create call from Rx. So let's go ahead and take it apart piece by piece. We'll go ahead and start off, and we'll just create this done signal that we can await on later to know when to finish normally and clean up. So this is like our observable completion. In the case where you have a stream with a well-defined end signal, you can complete this to let the observe function clean up and return, and we'll see that in a little bit. So the next piece here, where we're creating the location callback, this should really be no surprise. We need one to receive updates from the location provider. But what's interesting here is that we use launch to call the observer function on the same coroutine dispatcher that observe location was called on. Remember, the coroutine scope that we opened here carries along the dispatcher with it that it was called with. So we always know that we're going to call the observer in the same place that the caller wanted the information reported. So we cancel the old job from before and start a new one. We make sure that we call the observer while we're holding this suspending mutex. And this keeps things serialized to make sure that we don't have two calls to an observer active at once. We assume that on location result won't have multiple calls active at once either. So this is kind of an example of some of the things that if you're building one of these things yourself, this is one of those comparison things of like RxJava kind of does a lot of these things for you. But with coroutines, we have all the primitives to build it. We just need to do a little bit more of it by hand if we're putting one of these things together. So we register our callback, and then we await on our done signal. And since we never complete it, I mean, when does a location stream really complete anyway? This will go ahead and wait for the calling job to be canceled. So we remove the callback in the finally block, so it'll happen on cancellation. And then request location updates normally takes a looper instead of something like an executor, which is kind of unfortunate, because this pattern really shines when you can avoid an extra hop. So if you use like a direct executor that'll just go ahead and run the observer wherever the update happens on the incoming binder thread or whatever it is, it really kind of shines when you can avoid those extra hops, but you get the idea. So here's what it looks like in use. And if you take a look, this looks an awful lot like just a for each call on a collection, and it behaves exactly the same way. So since we used launch to call the observer block in the first place, if the inner block throws an exception, that means that the observe location call itself will throw an exception into that outer scope. We can just wrap this whole thing in a try-catch, and that's all of our error handling that we need to do. So it's a child job, so it'll cancel the parent scope with the exception as well, the same scope that wraps the whole of the observe location function body. So it'll resume from the await with the cancellation exception, unregister the location callback from the finally block from above, and all of this just composes. So you, again, can lean on all of these constructs of the language that you already know by just adding some of these suspending primitives.
Cool. So let's wrap up a little bit. So what's next? What's some action items for you to do? Well, the first is that, as you saw in the keynote earlier, we actually have a code lab specifically for coroutines. And that was released about 3 weeks ago, which is a really good introduction into coroutines and how to actually use it in your app. And secondly, read the manual. I don't like to do that usually, but the docs are actually really, really good. They're on GitHub. You can look at them. You can even edit them if you want to. But they're all very use case based. They're all like, I need to do X. How do I do it? So make sure to go and check it out if you are using coroutines. And that is it. Thank you very much.